rates of reaction. We're going to have to construct a data table with our concentrations of our reactants. So just to reiterate, what is our overall goal in this experiment? This is the reaction that we want to find the rate law of. This is called the persulfate ion. This is iodide, this is sulfate, and this is molecular iodine. So we're not concerning ourselves with the coupling reaction. So the persulfate ion will react with the iodine or iodine anion to give you molecular iodine and the sulfate ion. And we want to figure out the rate law. The rate law is going to be determined by rate constant K, which is something you'll have to figure out. The order of the reactant decay for this one, exponent A, and the order of the reactant for that one, exponent B. So you have to figure out A and B at a certain temperature along with rate law, constant K, because it's real data, so you may get some decimals. It's not going to be a clean zero order, first order, or second order reaction. So once again, the goal is to get K, A, and B for this reaction. So let's just go over our raw data once again. Utilizing experimental 1 volumes and conditions. You notice here the average duplicate was 167 seconds. At a higher temperature, experiment 4, under the same conditions, the rate, or excuse me, not the rate is something that you're going to solve. The time in which we saw a color change was 77 seconds. So, more than half decline in the time it required for the reaction to proceed. Kind of tells you that at a higher temperature, you get a faster rate of reaction as determined by the onset of the color. And then experiment 5, same conditions as experiment 1, we did it with a catalyst. The catalyst really, by a factor of almost 5 times faster. So here are the volumes, okay, for the corresponding reactions. Now, if you want to figure out the rate, you're going to have to go in your lab manual or in your lab handout, and you can see here the rate, the initial rate, is the change in the concentration, or excuse me, the concentration of the thiosulfate ion divided by 2 times the time. Well, the time is given to us here. For experiment 1, 2, and 3, we'll just take the average of those. Now, what is the concentration of S2O3 minus 2? Okay, the concentration of S2O3 minus 2 is the same for all 3 experiments. So it's 2 mils times 0.010 molar divided by the total volume. So the total volume for experiment 1, 2, 4, 6, 7, 9, 11. It's 11 milliliters. Same thing for experiment 2 if you sum up these volumes. It's 11 mils. And the same thing for experiment 3. If you sum up these volumes, it's 11 milliliters. So the concentration of S2O3 minus 2, the thiosulfate ion, is going to be the same. What really determines your rate then is the time, okay, the time in which the color change happened. So let's go ahead and solve the rate for 1, 2, and 3, those experiments. And then also, let's go back to our table here. We're going to have to figure out the concentrations in experiment 1 conditions, 2 conditions, and 3 conditions. All right, so as stated before, the concentration of S2O3 minus 2 is going to be 2 mils times 0.01 molar. That's the concentration in the bottle divided by the total volume. The total volume for all 3 experiments was 11 mils inside the test tube. So doing that is 0.00182 molar. So now let's figure out the rate. So let's do rate 1. Okay, so rate 1, the concentration of S2O3 minus 2 thiosulfate anion is 0.00182 molar. Okay, so you got to remember here the mils and mils cancel, giving you the concentration inside the test tube. So we got the concentration divided by 2 times the time for experiment 1. So going back to our data table here, the time for experiment 1 is, we'll just take the average value, 167 seconds. So we want to be very cognizant of our units here because rate is some concentration over time. So doing this on our calculator, so 5.44 times 10 to the minus 6, and then our units are going to be m over seconds, molar over seconds. And let's do the same thing for rate 2 and 3. The time for a color change for experiment 2 was 82 seconds. So we can put that here, put this here. Let's figure out rate 3. The concentration of this, it's the same for all 3 because it's 2 mils and the bottle concentration is 0.010. And for rate 3, our average time for the color change was 77.5 seconds. So 2 times 77.5 seconds, about 1.18 times 10 to the minus 5 molar per second. So we have our rates here. So we'll fill that out here. Let's do that really quickly. All right, so let's focus on our data table here. Now we need to figure out the concentration of persulfate and I minus. I guess this is called the iodine anion. So let's go back to our volume table here. All right, so once again, 2 mils was taken in experiment 1 of iodine, I minus. So the Na plus is the counter ion. It's not participating in the reaction. So the sodium and the potassium are what are known as spectator ions or counter ions. So we do not worry about them. It's not of our concern. Our concern here is the I minus that's participating in the reaction. So the concentration of the I minus for experiment 1 is going to be 2 mils. So the way I'm going to label this is the concentration of I minus for experiment 1. We took 2 mils. The concentration in the bottle that was given to us is 0.2 molar. Total volume in all of these test tubes, 1, 2, and 3, is 11 milliliters. So 2 times 0.2 is actually 0.4, and take that and divide it by 11. All right, so let's put that in here, 0.0363. Okay, the units are big M, moles per liter. M is moles per liter. That is actually, this is the I minus concentration actually. So this is the I minus concentration. But it turns out that if you look at the S2O8 minus 2 concentration, okay, I wrote the same thing here because it's also 2 mils times a 0.2 molar. So we can do the exact same thing for S2O8. This is called the persulfate ion. For experiment 2, it's the same 2 mils of a 0.2 molar concentration. Total volume is still 11 mils. So it's going to be the same thing for I minus. Okay, and it's double the volumes, keep the same concentration. So we're going to double 0.0363 M, right? So instead of 2 mils, it's 4 mils. So 4 mils times 0.2 divided by 11 is just double. For I minus, 4 mils times 0.2 molar. So for I minus, it's going to be 0.0727, right? You see how I'm getting that? Experiment 2, it's 2 mils. Experiment 3, it's 4 mils. So you're just doubling the concentration. And then S2O8 is, we're going back to 2 mils. So it's going to be 0.0363. All right, so there we have it. We figured out our rates. Okay, so this came from the lab handout. Okay, no derivation, nothing, just take it straight from the lab handout. And then plug in your values from the times that you got. Fill in this concentration table utilizing this formula. It's easy because all the volumes are 11 milliliters, and all we did between experiment 1 and 2 was we doubled S2O8 minus 2, and in between experiment 1 and 3, we doubled the I minus. So now we can go and do the actual analysis, the rate law problem that we've been doing in class. All right, so we're going to compare experiment 1 with experiment 2. And so we have rate 1 is 5.44 times 10 to the minus 6. Okay, I want you to put those units in. Those units are going to be very important. It's not something you can omit. And remember that lowercase k has different units depending on the problem. So the units of lowercase rate constant k are going to vary. So rate 1, experiment 1 was that. Rate 1, experiment 1, concentration of this persulfate is 0.0363. Okay, that's to the power of A, and then I minus, again, is going to be 0.0363. We're going to make that to the power of B, the order of decay for that reactant. All right, rate 2, experiment 2. Rate 2, we calculated it from this formula to be 1.11 times 10 to the minus 5. So let's put that in here. Rate is equal to K times the concentration of S2O8 minus 2 for experiment 2 was 0.0727 to the power of A times 0.0363 to the power of B for the I minus. All right, so immediately we'll see here that the k's cancel. This whole thing to the power of b cancels with that whole thing to the power of b in our rate law comparison. So we have 0.036 divided by 0.0727. That's 1/2. That whole thing gets to the power of a. Okay, so what we need to do now is figure this out. The m over s seconds cancels out with the big M over s seconds. So we need to figure out what this is. Let's see if it's so clean. 5.44 times 10 to the power of minus 6 divided by, I like to put my parentheses in, 1.11 times 10 to the power of minus 5. And 0.49, so 0.49, that's actually very close to 0.5. So that's a tough call. You know, I'm tempted to just round that up to 0.5 and say a is equal to 1. But let's just go ahead, realizing everyone's data may be a little bit more different. So natural log of 0.490 equals, so if you take the natural log of the number with the exponent goes to the ground, so to speak. All right, so this is derived from the natural log rule that this is not something, you know, this is not a math class or a trigonometry class, but that's just a rule of the natural logs. Again, you know, if it was 0.5, we easily just say a is equal to 1, right? So 0.5 equals to 0.5 to the power of 1. It's 0.49, so we'll just, because I know some of you may not get such easy numbers, maybe you get numbers or values that are difficult to work with. So anyways, natural log of 0.490, let's take the natural log of that. Natural log of 0.490 is minus 0.713. Let's just put a couple of extra digits here, and equals a times natural log of 1/2 minus 0.6931. The minus signs and minus signs will cancel each other out. So a is going to equal to 0.71334 divided by 0.69314. Let's put that in our calculator. And there we have it. Okay, so that's very good. We got our first order of the reactant. You know, I knew it's going to be close to 1. And A is going to be 1.02, 1.03. All right, now, so this is roughly about first order decay for the persulfate ion. What's the order of decay? B for I minus. This time around, let's compare experiment 1 and 3. I think you can experiment with either, you can compare either experiments, it really doesn't matter. I'm just looking at these raw numbers to see which ones cancel out, and because we want I minus, I feel that comparing experiment 1 and 3, we can figure out the exponent B for I minus. All right, so 1 and 3 is next on tap. So experiment 1 is 5.44 times 10 to the minus 6. All right, equals rate constant K, rate 1, experiment 1. We're going to have to find that out at the end of this problem. S208 minus 2 is 0.0363 for experiment 1, rate 1 to the raised to the power of A. We already found A, but you'll realize that they'll cancel each other out. So that was the advantageous reasoning behind comparing experiment 1 to experiment 3 here. I minus for experiment 1, rate 1 is 0.0363 to the power of B. All right, so now we're going to do rate 3, experiment 3 conditions. S208 minus 2 for experiment 3 is 0.0363 m to the power of A. And for I minus, it's going to be 0.0727 molar to the power of B. All right, so plugging in those appropriate concentrations for the appropriate experiments. The lowercase k rate constants cancel, these units cancels, this whole thing to the power of A cancels with that whole thing to the power of A. We already figured out the order A, so it's really a moot point. And this over this is 1/2 to the power of B. Okay, let's compare these two rates and see if we get a clean answer. Take the natural log of both sides to solve for that rate order of the reactant decay for B. In order to do that, we're going to follow through with the same math. We're going to take the natural log of both sides of the equation. So the natural log of 0.461 equals, so if you take the natural log of the exponent goes back to the ground. So it's going to be natural log of 0.5. So b is going to be the natural log of 0.461 divided by the natural log of 0.5. So let's do that on our calculator. 17, we'll just go 1.12. And like I stated before, you know, on any exam, hopefully on the test question, you'll just have easy numbers, straight decimal point, 0 or 1 or 2 for 0 first or second order decay.